Welcome everyone at our TDS webinar. This is the second webinar this year, and it's my great pleasure to introduce Professor Sue Campbell from the University of Waterloo. As we just discussed, we got in touch with each other about 25 years ago when she sent me some of her papers on Hopf networks with time delay. And now 25 years later, Hopf actually got a Nobel Prize for his original contributions. And I think also if you want to work on coupled systems with time delays, you will sooner or later going to meet with some of Professor Campbell's work. And I always like to listen to her talks, and had the opportunity to do it a couple of times on TDS conferences and also in some other workshops. Today she's going to talk about indeed time delays, Hopf bifurcations, and synchronization. So without any further ado, Sue-Ann, the floor is yours.
Thank you so much, Gabor, and thank you, Gabor and Wim, for the introduction. The TDS community, I really feel, is my home community in a lot of ways, with working on time delay systems, and over the many years of different conferences where we've gotten together. And this is such a great initiative to help keep people connected. One of the things we learned over COVID, right? How to keep people connected, even if we're in different parts of the world. So thanks again for the invitation to speak. So this may be review for some people that have seen it before, but anyways, it's sort of a little retrospective on some things I've been thinking about. So here, sorry, there we go. Yeah, so just to give you a little bit of background about what I think about. So things that motivate me are thinking about neural networks and biological neurons. And this is just some pictures of sort of a schematic of a neuron and some images of neurons. And so they're the fundamental kind of unit of processing, information processing in the brain. And how they do that information processing is primarily through electrical activity. So if this is another image of a neuron, can you see my mouse okay? Yeah, okay, great. And so this is the cell body, and you have all this axon dendritic tree, which is where it connects with the other neurons and it makes their communication. And if you put an electrode in that cell, you can measure a voltage difference across the cell membrane. And what this is, these pictures are showing from different cells. On the y-axis is that voltage difference, and on the x-axis is time. And this is just showing how, and these are, as I said, different types of cells, that can be periodic behavior. So that's fundamental signal. The spike of voltage is called an action potential, and it can occur spontaneously. Here you have what's called bursting, where you have sort of some spikes and then lower activity, and spontaneously rhythmic oscillations, or these ones are basically forced, where there's some input put into the cell and forces it to oscillate. But the key idea is that they can be very periodic behaviors. So I tend to, when I think about things mathematically, these neurons, I think a lot of them, I make a lot of use of literature about oscillators and coupled oscillators. And when you put them together, networks of these neurons can exhibit coordinated activity, either transiently or more lengthy. And so this is some measurements. This is a hippocampus in rat, I believe. And these are different electrodes, different colors at different spaces. And the little ticks here are just showing when that little spike occurs. So this is at the pink electrode, the blue, and so on. And then they sort of regrouped them here. This is time, sorry. And this is, again, this is sort of neuron number. And they've regrouped them, and you can see how they can sort of come together, sort of synchronously, maybe transiently synchronously, or maybe more long term. And this is a similar kind of plotting in a different region, and the colors are different regions. And again, you see here you can sort of see the voltage versus time for each little cell, and you see these coming together of synchronization. If you look at much larger networks, such as EEG, which is measuring electrical activity like on the skull or directly on the brain, you can see, again, these sort of large, these frequency oscillations going on, various frequencies occurring. And some of those are natural frequencies that occur with different behavior, but you can also have ones that are occurred with disease. So this is associated with epilepsy, where you see kind of a low behavior, and then you have very highly synchronized behavior across many electrodes, which is not a normal situation. So this is just, again, the things that make me, that motivate some of my work is looking at these models for neurons, and then thinking about how does, if we have can have oscillatory activity at the single neuron, how does that turn into coordinated activity in a network? What's the role of the structure of the network? And of course, a lot of my work is thinking about signal propagation delay, because it does take time for the information to translate from one neuron to another. Some of it's just time to travel along all those little dendritic branches I showed in the picture before, and then also there's some chemical reactions that have to occur. So what I want to talk about today, given the time, is just some kind of long-term work. One is this idea of cluster synchronization, which comes out of the physics literature, and then also out of the sort of symmetric bifurcation literature. And so I want to look at that from the point of view of delay-induced Hopf bifurcation in a sort of a general class of models, and then look at some applications. And then the second thing I want to think about, which is kind of related because we'll see again Hopf bifurcations come up, how time delay can be important in thinking about desynchronization in a network. So maybe if it's synchronized and you don't want it to be synchronized, or how it can lead to desynchronization. So the cluster synchronization, this is some very old work by a really talented PhD student of mine who looked at this in a couple of contexts, but this is a particular paper. And again, the motivation here was those pictures that we saw before of what is called neural assemblies, where groups of neurons come together, are almost synchronized. Then you might have different groups, and those might activate in some kind of sequence. It could be linked to a stimulus, and neurons can belong to different of these assemblies or groups. And how that kind of links to the idea of cluster synchronization of coupled oscillators, where the oscillators separate into groups, and they can be in the same group, they're phase locked with zero phase difference, but in different groups, they're phase locked with non-zero phase different. And then you could have different clusters of states that kind of group the oscillators together in different ways. And so we were thinking a little bit about, how can we have these cluster states? Can we switch our network between different cluster states without changing parameters? So is the possibility for multi-stability? And really, what's the effect of network connectivity and structure and time delay on these kind of questions? So just to give again just a picture, this will come back to kind of where this comes from, but what I'm thinking of is this is a little example with 6 oscillators, and I've given them each a different color. And they can be arranged in lots of different ways, but these sort of phase-locked cluster things I'm thinking about, you could have them all spread out across the period. So you can see they're more or less, especially by the end of this, spread out across the period. So there's a 6 cluster, they each have their own. They could be all grouped together, so they're right on top of each other here, they're synchronized, so it's like a 1 cluster, everybody's in the same cluster. And then you could have them breaking up into, so here I have 2 clusters where there's 3 neurons in each, and 3 clusters where there's 2 neurons in each. So you can see this kind of same network. I think in this case I changed a parameter, and we could go to these different kinds of behaviors and have these different groupings of the neurons. So the model that Jeanne looked at in her work, because we were trying to make this kind of general, was to look at the sort of generic form of neural models, so basically conductance-based neural models, which tend to have this form. So the voltage variable, which I mentioned before, which is the measurable variable, has an equation that, so in the absence of coupling, so this is going to be the coupling term, depends on itself, and there's some nonlinear function, and then it depends on these other variables, which are called gating variables, that have to do with basically the biophysical mechanism for producing the action potential. And then so each neuron has some equation in this form, so these are just nonlinear differential equations, and then they're coupled together typically through the voltage variable. So there isn't typically coupling between the auxiliary or gating variables. So you have this kind of structure, and here we're thinking about putting a time delay, so it takes time for the information from the jth neuron to get to the ith neuron. And the coupling framework we put on here was circular coupling, which gives some symmetry to the system, but it also includes some nice sort of subsets you can think about, like all-to-all, or nearest neighbor, or distance dependent. So it's kind of a general framework that we can apply to different situations. And this mu I'll mention it a little bit, but this is a parameter which switches the state of the uncoupled neuron. So here's my uncoupled. There's some critical value where it goes from being at a stable equilibrium point to a spiking situation, right? So there's different parameters that can play that role in the model. Primarily, I'm thinking here of situation where the neurons are at rest, and then when we couple them together, really the coupling can bring them into a spiking situation, but they can be intrinsically oscillating, and you can think about it in different ways as well. So the way we looked at this, because we have some symmetry in the system, is so we assumed, which is pretty common in these models, that there is a sort of synchronous equilibrium point. So there's a starting equilibrium point where all the neurons are doing the same thing. So this would be like they're all sitting at the resting membrane potential, which is what they tend to do when they don't have any input. And so we could go through and do look at the characteristic equation of the linearization around the synchronous equilibrium point. And now going, that's all pretty straightforward. But because of the circulant coupling, that has a very nice structure to it. And so that characteristic equation, we have something involving, basically there's a product of terms, and each of those terms looks like the determinant of a matrix here. So this is identity matrix. A and B are just the Jacobian matrices of our sort of individual neuron model with respect to either X or the delayed version of X. So the structure comes out, as I said, of the circular coupling, and the key point is so these A and the B are the same in each of these terms. And we've just made a simple same delay everywhere for this one. But where the coupling comes in is through this delta K, which is the eigenvalues of the connectivity matrix. So you get this sort of product of terms where the main difference is comes from the different eigenvalues of the connectivity matrix that you started with. Okay, and here, because we had a circular matrix, we had this particular form for those. So if we look at delay-induced Hopf bifurcation, then we're just, this is kind of standard. You look for pure imaginary eigenvalues, and then we can break it up and think about like each of these terms in turn. And the idea is they're very similar. The only thing that's kind of changing from one to the other is this delta K. So you can kind of write down a framework for that. So some complicated expressions here. But if we want to think about, when do pure imaginary eigenvalues occur as a function of the delay, so we can take this and do some manipulation, and then we can solve for these critical values of the delay. And so the K here refers to kind of which factor we have the pure imaginary eigenvalue in, and the J just refers to the fact that it can happen multiple times, right? When we have a strict discrete delay like this, when we have one pair, as we increase the delay, we can have multiple versions of that. So you can kind of map this all out, just where you get these delay values, where you have pure imaginary eigenvalues, and then you can apply some standard Hopf bifurcation theory for delay differential equations. So if the model's circulant but has no other structure, so the model has Zn symmetry, then you have a sort of a few standard things that we have a characteristic. The characteristic equation has a simple pair of pure imaginary eigenvalues at this critical value. The other roots are not resonant, so the non-resonant condition, and this is the non-degeneracy condition. You can kind of write down what we need to satisfy in terms of that general situation. Then you can show the model undergoes a Hopf bifurcation of the equilibrium point at each of these critical values. So this is just using some standard theory for ODEs and self-delay equations. And then you can start to think about not just that there are these Hopf bifurcations, but what do the solutions look like? So this is where we're getting into using some of these ideas of symmetric bifurcation theory. So this is quite classic work from Golubic, Stewart, and Schaper. And then this is Junhong Wu's work that kind of extended that to delay differential equations. So if you look at these individual taus and the K they're associated with, which has to do with which particular eigenvalue of the coupling matrix, then you can show what the form of the solutions will be. So if you take the K as 0, 1, all those critical delays give you bifurcations that give synchronous solutions. So you're going to get oscillations where all the neurons are it's synchronized with each other. And then there's sort of two other types. If you have a K that's relatively prime with n, the number of neurons in the network, then you get the solutions where the oscillators are all spread out. This just means they're spread out equally across the period. So that was that in that example we gave with the 6 neurons, that was the 6 cluster solution. So they're equal, sort of evenly spread out across the period. And the last is the interesting case where K and N have some common factor. And this is where you can get the bifurcation to these oscillations where they spread out into these groups. And so this is just a complicated way of saying they're in these different groups. You can figure out which neuron is in which group. And then this is talking about the phase difference between the different groups. And so this is the N cluster periodic solution. So in the little example was the cluster of 2 clusters of 3 neurons or 3 clusters of 2 neurons. So you can kind of map out exactly what's going to happen with these different bifurcations just by looking at your structure of your connectivity matrix and thinking about the different what's the size of N and the different kind of factors of that. So if you have a little bit more structure, so if say it's circular and symmetric, then you have DN symmetry, and there's a little bit more work to do on it where you have to think about equivariant Hopf bifurcation, and you can have other kinds of patterns of oscillations like standing waves that I'm not going to get into today. I'm mostly thinking about these cluster solutions. So I want to, so that's the basic framework that Jeanne kind of laid down in her thesis, and she did some applications. I'm going to look at one just to kind of see how this plays out. It was a Fitsu-Nagomo model, but then I want to talk about another more recent work where we've done a network with excitatory inhibitory coupling, where we really see that the same framework kind of applies. So the Fitsu-Nagomo was a kind of simple 2-dimensional model. X is kind of like the voltage variable on this, so it's like sometimes called the activator, and Y is kind of like a gating variable. It was not as biophysically motivated as some of the others. And here she looked at delayed diffusive coupling, so just a simple difference of the terms. And the mu parameter here, yeah, when you vary that, you can have, so this is just a bifurcation diagram, X versus mu. The red is stable equilibrium points, and the green corresponds to stable periodic oscillations. And this is, so as I vary mu, I can go through that. And so there's always this equilibrium point here. It can be stable or it can be unstable. And you can go through and apply all this theory that we're thinking about and just looking at the different bifurcations that can occur. So I'm going to just walk through that. So this is N6, which is really related to that. Those are simulations I showed at the beginning. So we've taken some particular values. This has got distance-dependent coupling. So it's circulant, but as neurons get further apart, the coupling gets weaker. And there's 2 values of the mu. One is actually where, let me get this right. Yeah, so this one, the green corresponds to the equilibrium point being stable. So this is actually where without coupling the equilibrium point stable, and in this case, without coupling, they're actually oscillatory. And so what I mapped out here, the colors are just, in this case, we just mapped out those various Hopf bifurcations that I mentioned you could have. So in the N6 case, we could have synchronous Hopf. And so this is the delay as a function of the coupling strength. So along these curves, these are where Hopf bifurcations can occur. And the coloring is mapping out these different ones that I had in general on the previous page. So the green is the 6 cluster, magenta is 3, and blue is the 2 cluster. And she did work on sort of where there's supercritical and subcritical. And so the interesting, so you have this repeating behavior, which you expect with the delay, but you have this kind of interesting interweaving of these different curves. And you can see, for instance, in this case, if I take a particular value of the delay, depending on when I change the coupling strength, depending on what the delay is, I may go through here, which would give rise to like synchronous oscillations, or I might go through here, which would give rise to one of my asynchronous oscillations. And the interesting thing, even when the neurons are intrinsically oscillating, you can have these bifurcations that basically kind of turn off the oscillations. It's really like the Hopf is going this way to give the oscillations. So again, you can see all these different kinds of possible oscillations depending on the size of the delay and the coupling strength. And then, so that's great. You can kind of map that all out. And but what's really interesting is that there's all these intersection points of these different Hopf curves. And so what that means, right, is where these cross. So one of these curves, I have a pair of pure imaginary eigenvalues, and in one of my factors from that in my characteristic equation, and at the crossing point, I have two pairs, one in one factor and one in another. Oh yeah, sorry, this is just showing the simulations of the difference of synchronous, 6 cluster, 2 cluster, and 3 cluster. But the interesting is where you have these intersection points, then you can get interesting. So this is a double Hopf bifurcation. There's lots of work about that. You can get things like bistability. So let's get this right. This one is around here, close to the synchronous, which is subcritical and gives rise to actually quite a large amplitude oscillation, and the 6 cluster, which is supercritical. So this is actually a really little low amplitude 6 cluster. And we have bistability, so we can switch. We just put a little input into gave a little perturbation to a few of the cells, and we can switch back and forth. So it's kind of very striking where you can make this network to go from this very high amplitude synchronous to this kind of low amplitude asynchronous solution. And the other thing, of course, you can get out of these intersection points is interesting quasi-periodic behavior. So this is some kind of torus solution. So you can see the modulation of the amplitude, but you can also see that it's running through the different neurons, right? So we start with one neuron, the other. So there's also this kind of sequence of, as you can see, it's sort of associated with this 6 cluster solution, and then there's a torus bifurcation. So kind of very interesting out of these intersection points, the fact that you can switch between these different cluster solutions and off between synchronous and asynchronous, and then also that you can kind of get these complicated quasi-periodic solutions. So the second application of that I want to think about, and this is just, I'll be a little bit more brief about this, but it was really something more recently that I did with Huayan Ru from Elon University. And we realized that, a common network structure in the brain. So all the previous work was on neurons that were the same type, coupling of the same type, so they would either be excitatory or inhibitory. But there's a common structure where you have local circuits where excitatory cells have their kind of local inhibition that they're connect to. And then on a more large range, the excitatory cells are coupled to each other. So this happens, say, in the cortex. And so we have kind of local coupling and then more long range coupling. So we said, okay, we're looking at this where we think about just putting the time delay here in the long range coupling. And so this is what we did, and this is a model that we put together. So the red is that delayed coupling term between the different E cells. So like EJ goes with EJ plus 1 mod the network size. Here we just looked at 2. And so the interesting thing is because the coupling is only going through this is like our voltage variable, and this is like our gating variable, going through the E cells, even though I have 2 types of neurons, the little the sort of subnetwork of excitatory inhibitory, when one excitatory, one inhibitory cells really acts like its own little unit. And so all the black stuff is kind of within a unit, and then the red is connecting between the units. And that really means that we can apply that same framework that we had thought about before and just sort of think about our neuron now as being this little unit that actually has an excitatory and an inhibitory neuron. And again, this is just a simple model. Here, the applied current. We use the same model for excitatory and inhibitory cells in this setup. And the applied current, again, that's a kind of standard parameter in these models. So I ramp that up. I go from, again, a stable equilibrium point to having some oscillations. This is through a subcritical Hopf. So this is some green is, again, stable oscillations. And then if I make the amplifier big enough, I turn those oscillations off again. But we're really thinking about actually being way over here. So we wanted to really think about what if I just coupled these together and there's no applied current and all the inputs basically coming from the coupling. So when we did that, and this is with no delay and no input, so these guys are off. So all the equilibrium points are just at their own, all the neurons at their own equilibrium point at rest. So this has a really nice, interesting structure because even with no delay, there's some bistability. So this is the strength of the coupling between the different excitatory neurons, so between the different kind of nodes. There's always this low, this is kind of a normalized model, but this is a low voltage level. So this is like a resting potential. And if there's enough coupling, then we get, this is basically a saddle node bifurcation, and then you get a little subcritical hop, and then you get this high amplitude equilibrium point. So there's some bistability here, but there's no oscillations when there's no delay. It's just you can have either, if there's sort of low coupling, then you just have rusting, and if you have high coupling, then you can switch between the two. And then, as I said, this little subcritical Hopf that doesn't really do anything except for change the stability. But it's when we put in the delay, then we can do the same kind of analysis as was done before and think about these delay-induced Hopf bifurcations that give rise to oscillations. And this is same idea as that other picture. I'm mapping out the delay versus the coupling strength between the E cells, so between the different units. Here there, as I said, this is just a kind of simple case where we just had two neurons. So there's a sort of two basic things. They can be synchronous, so they're oscillating the same, or they can be in this sort of antiphase two clusters, so situation. And so that's the red and the blue. And then the gray actually had to do with bifurcations of there's other equilibrium points that aren't unstable, so they don't really do much. And so again, we can see this structure of these different branches of the synchronous and the two cluster solution. This is using DDE-BIF tool to kind of follow some of them. Most of them are so this is unstable. Most of them have this kind of interesting structure that they're subcritical and they loop over and become stable. And this is just at different delays. But again, the one thing I wanted to point out here again is you have this crossing. And so I think this is a parameter value sort of in here, where we've got two solutions. One, this is the antiphase. So the red and the black are the X's, the excitatory cells, and the green and the blue are the inhibitory cells. So we have this sort of antiphase behavior, and then here there's an in phase where they're in phase. Here the amplitudes are somewhat similar of the two, so we can switch in this region close to where these are intersecting. We could switch between these two different behaviors. So it really gives the network some flexibility, and it's just, here I did it with changing initial conditions, but you could do it just by giving some input to the network and letting it switch. So this is more sort of, I mean, just to point out that that same framework can be applied to a little bit more general structure, which is more biologically realistic. So yes, it's the second part of the talk. I want to think a bit, it's another project that was with a kind of group of people over time. So it really started with Wilton Nicola, who was a former PhD student, and then Liang Chen, a PhD student, and Isam, who was a postdoc, but then at that point was in his own position, and Bhutan Raman. We all kind of worked on this at various stages together, and there's a sequence of papers. And I won't probably get through all of it, but I want to sort of, again, there's a kind of key similarity that comes out of this. In this case, thinking about some desynchronization. So it's a similar kind of framework to that last model. This is the kind of network framework, and I think I have it on here, yeah. You have excitatory, now we're thinking of sort of an excitatory population and an inhibitory population that interact locally, and then there's some global connections between different nodes. So this was first set up by Hellyer et al. they had a model, and they used the Wilson-Cohen model. So the idea here was this more population behavior versus individual neuron behavior, but again, similar structure to that last model. And there they had a bunch of nodes, I think it was like 400 and something, and they connected them using this as data on how different regions of the brain are connected together. So they set these nodes up, and they had a kind of a node per region, and they set up the whole model, and they put in time delays, and they saw sort of complex behavior and transitions from synchronous to asynchronous. As I said, they had delay, they had connectivity, different connectivity, and Wilton and I kind of started talking about this, and he got me interested in one. They were also interested in understanding kind of where this comes from in the model, because they kind of put together this complicated model, and then they, what is it about the structure that's giving rise to that? And so here's some of the references about that original model. So just to give you a sense of what it is, so as I said, it's a network of Wilson-Cohen nodes. So there's one variable for each. A bunch of nodes. Each node has an excitatory population and an inhibitory population. And so the standard Wilson-Cohen node would just have that, and they're connected together. We just have excitatory feeding into inhibitory, local inhibitory feeding into the excitatory, and then these global connections with delays between the excitatory nodes. The kind of novelty of what they put in was they had homeostatic variation of this inhibitory weight. So the idea of this was that to keep the network from getting too excitable and kind of runaway excitation, they allow this to be varied. And basically the setup here is if the excitation gets too big, it's trying to kind of keep the excitation at some level. And if the excitation gets too big, these nodes, the weights get turned up, and there's a negative here. This is going to kind of turn down this and make the excitatory population level go down. Okay, and so the weights are all non-negative. The E and I's are supposed to be sort of representative of proportion of activity, so they're between 0 and 1, and this phi is a sigmoidal variable, so we take it as a logistic. So we can do the same kind of idea right here, because again, the nodes are all identical. And if in this case we take a slightly different idea, we don't have circling connectivity, but we just assume that there's a row, so they all have the same row sum condition, which is basically saying each node has the same amount of input. It could be coming from different, it could be different ways of connecting, but the kind of total input that it's getting is the same. We'll call that WE. And then you can take your connectivity matrix and kind of scale that out. So under that condition, you have a synchronous solution, and that synchronous solution is just described for a single node with delayed self-coupling. So you get just this little self-coupling. So you can do a lot of analysis on that, which I'm going to go through fairly quickly. The key point is that you have a Hopf bifurcation. So this is in the excitatory coupling between the nodes, and this is the excitatory to inhibitory coupling within a node. And this is where you have a Hopf bifurcation as you sort of increase that. So it's kind of very broad. If you have strong enough coupling between the nodes, you can get this even without delay. And then actually, as you increase through there, you see a period doubling behavior and some quite complicated behavior. So this is taking, I think that's kind of swath up here. You go from little Hopf bifurcating periodic orbit, period doubling, and some quite complicated behavior. And when you have a small delay in the network, you see pretty much the same behavior. So here's the green Hopf curve, and the black are these period doubling isolas that sit above that. But if you increase the delay, just not very much to 0.4, and this is sort of in the biophysical range in terms of how we sort of scaled things, you wipe out all that behavior. So we go from the green, where we have these period doubling cascade, the blue, when we turn on the 0.4, it just wipes out all the complicated behavior, and we really just go from kind of standard Hopf to this kind of like a canard thing, where you go to a large amplitude relaxation oscillator. So we thought it was kind of interesting because the delay actually wipes out the complicated dynamics in this sort of synchronous solution. And so the question is, what happens when you put it in a network? And so if there's no delay in the network, the observation is that smaller networks, so we looked at a bunch of different types of coupling, smaller networks, the blue means we're plotting like all the different nodes on top of each other, and I'm trying to make there's like 20 or 30 here. Well, it depends on sort of the size here. Blue is they're all synchronous, so we just see everybody on top of each other, and the multicolor is where we see more asynchronous behavior. So the nodes are doing different things. And so the smaller networks tend to synchronize, the larger may desynchronize, but it was really, this is changing the coupling strength. So it was really dependent on what the kind of local behavior of the node was, and it seemed to be desynchronization was sort of associated with the KDOC behavior. So our thought was, well, if we put in the delay, the synchronous solution, we know when we put in this delay, it kills that complicated behavior. So maybe we'll just kill this desynchronization with the delay. So we did a little bit of work with the master stability function, but I think I'm going to skip that. Not go into a lot of detail, other than to say that we saw a kind of interesting dual effect of the delay. So when you turned on the delay, it could be desynchronizing or synchronizing, and it really depended on the eigenvalue structure. And I'm not going to go into detail, but let's go to master stability function type of behavior. And I think I've just got some simulations to oscillate that. So this was a lattice model or weak coupling. So lattice model has real eigenvalues. Weak coupling is sort of the eigenvalues are small magnitude. And as we increase the delay, I mean, this is what we were expecting from the single node, is like we're sort of simplifying the behavior and things just stay synchronized. But when we looked at, and this was what was predicted by the master stability function, if you look at a connection matrix where you have complex eigenvalues where the magnitudes are large enough, and here these were ring networks, 7 and 8, what you could see is as you increase the delay, especially here with N7, first you see this sort of simplification of the behavior. So it went from sort of maybe chaotic to just oscillations, but then as you increase it further, you get more complicated behavior. And as you increase the network, you see that kind of complicated behavior coming earlier. And actually, this is desynchronizing. So here they're synchronized. If you look at those in some detail, what you see is that in that sort of bubble where it expands, again, the neurons all have different colors. They all kind of spread out. So in the sort of low amplitude, they're kind of crushed together and synchronous. And then in here, they're kind of spread out across, and then they kind of crush together again. So this delay could be synchronizing or desynchronizing when you put it in the network. And so that was great. And we kind of predicted that from the master stability analysis, and we confirmed it with simulations, but then we wanted to understand, like, why is that happening? And this is where we kind of link back to the previous work. So we can do the same kind of analysis where we look at a synchronous equilibrium point and do the linear characteristic equation of the linearization. And again, because we had that constant row sum condition under a little bit of, well, basically assuming that the connectivity matrix is diagonalizable, you can still do this breaking up of the characteristic equation into these terms. And here I'm giving a little more detail, but this is basically the same thing as we saw at the very beginning of the talk, where these terms are really coming from the local structure of the individual nodes. So it's three-dimensional because I have 3 variables in each node. And so it's like where the power 3 here is coming from. And then there's some terms coming from the coupling. And again, the only difference between the different terms in the product has to do with which eigenvalue you have. The eigenvalues are coming from, this is the scaled connectivity matrix. So we factored out this W8 because of the constant row sum. So when we look at the eigenvalues of that matrix, then this is what's determining. And of course, that fits right in with the master stability function, right? Because the master stability function works on the eigenvalues of the connectivity matrix. And we were just really trying to understand, like, what's the sort of bifurcation structure giving that change to the synchronization and desynchronization. Okay, and so the key point, if we think about, again, the types of solutions that you can get out of this, so k is equal to 0. That gives RK is 1, and that just gives the bifurcation sort of within the synchronous solution subspace, so that gives the rise to synchronous oscillations. And the other Ks in general are going to give rise to oscillations that are asynchronous. So you expect that the nodes to be oscillating, but doing not perfectly synchronized. And so we looked a little bit at how that structure of these Hopf bifurcation curve depended on, again, these synaptic strengths and then also the time delay. Okay, I'm not going to bother. You can write out some nice fancy equation model for that, but let me just look at the pictures. So this is the same structure I had before. This is the strength of the coupling between different nodes, and this is the excitatory to inhibitory coupling within the node. And the black curve is that same Hopf bifurcation that we saw when I had one node that was describing the synchronous solution. So this is the Hopf bifurcation that gives that synchronous solution. And when we look at the other parts of our characteristic equation, they give rise to just other Hopf curves, which are actually have a very interesting similar shape to them. And in this case, we sort of took some very simple ones because of what we saw with the master stability function. We wanted to take simple case where I had either real eigenvalues or complex eigenvalues, because those seem to be kind of a switching point between the different cases. And so here I did a bidirectional ring. If you change, this is different values of k. You can see, so the red and the blue would be these asynchronous Hopf bifurcations. The black would be synchronous. The equilibrium point's stable down here. So as I increase the coupling, I expect to get oscillations as I move up here. And the key point is that these asynchronous, these colored ones, are always above the synchronous, which means I'm going to cross the synchronous Hopf first. And that's going to be, after that, the equilibrium point's unstable. So it's not clear that these ones are really going to affect the behavior. And if we increase the number of neurons, we can get more of these curves, and they can move down closer, but they always stay above. So that's kind of a key thing to keep in mind. And then if we put in complex eigenvalues, we get a little more complicated structure. This is a unidirectional ring. And as I change either the k or increase the number of neurons, what I can get is to a situation where, I think I've got 15 here, yeah, where I can have these intersection points. And so the key point here, right, is depending on where I am, I may now cross the asynchronous Hopf curve before the synchronous. And so that's going to be the one that's determining the behavior. And so here we could start to see this effective network size that we saw. This is even without delays, right? If the bidirectional ring, it doesn't really matter the network size, the curves always stayed above. So that was similar to what we saw with the lattice in those simulations. And the unidirectional ring, depending on the network size, they can, if it's big enough, you can have these intersection points. And so the idea we thought, okay, the mechanism for desynchronization is the fact that you have these intersection points, you have double Hopf points, you can cross these curves, the asynchronous Hopf before the synchronous Hopf. And so you can see this is just a simple asynchronous oscillation. So the neurons are all spread out. There's 10 of them and they're all spread out. So this is this kind of splay solution. But because of these intersection points, you can also see kind of a kind of synchronous modulation on that, which gives you a torus, which again, we're kind of changing the W, can lead to these more complicated solutions. So we can kind of see how these complicated solutions could arise. So then the last piece, I'm just making sure, okay. The last piece of the puzzle was to think about, okay, what happens with the delay? So this can happen without delay, but the key point is if you now add delay between the nodes, it doesn't really affect the curves with real eigenvalues. It actually will sort of raises them up, but you see there's still the structure. So the solid curves still lie above the black curve. So we don't really expect too much change there. But when we have the complex eigenvalues, it can actually bring those curves down. So you can have intersection points when you have the delay that you didn't have before. And so it means essentially you can get the asynchronous behavior for smaller networks. Yeah, so that's it. So you get desynchronized behavior for smaller networks. Okay. And last little bit, we did look a little bit about distributed delay, but I know I'm getting short of time. And the key point there with distributed delay, if there's a small kind of mean delay, we don't have much of an effect. But if we get a larger mean delay, then it can really depend on the distribution. And then these are getting out of sort of the biophysical range. But the key kind of idea here with the Dirac, so this sort of fixed delay, discrete delay, we kind of maintain this asynchronous behavior. So these curves are lying below. Whereas with the weak gamma or strong gamma, we could actually see as we move the delay, the curves, the little dash curves kind of move down, but then they moved up again. And so here we're actually back to a situation where the synchronous could be dominating again. So the delay could kind of cause desynchronization, and then if it gets bigger, it causes synchronization again. Okay, and just a few comments. We use really simple network connectivity to look at these, but the results could be applied to any network that had these, where the matrix had constant row sums. We did do some simulations with heterogeneous delays to kind of see the behavior applies. And of course, this approach could apply to other network models. So I'm just going to finish up. The key point, right, is these delay-induced Hopf bifurcations, when you have these structured networks, can give rise to different cluster types, and the cluster types are really determined by the eigenvalues of the connectivity matrix. So different connectivity matrix, different eigenvalues could give you different solutions. And in this case, we had the sort of synchronous and then often these cluster type solutions. And so if we look at how our analysis of how these Hopf bifurcation curves, the structure depended on the eigenvalues of the connectivity matrix, really gave us insight. So we had these results from the master stability function, which are really clear on how the eigenvalues affected it. But this kind of gave us an insight into where that was coming from in terms of these Hopf bifurcation curves. And we had these interaction points, which we saw in all the situations, these double Hopf bifurcations that could give rise to cluster multi-stability between these cluster solutions, or these kind of complicated torus solutions. And so this gave this way of these interactions gave ways of desynchronizing. So in this last one, it was a desynchronization kind of through a torus type solution, or this complicated. But in the other model, just the 2-neuron EI, we had this where we had the switching behavior where we could just put an input and switch it from a synchronous to an asynchronous oscillation. So I want to acknowledge the contributors. So this is Zhen and Wilton from many years ago. There's Huayan, and here's Isam and Liang and Bhutan. So all the many contributors, and of course all my students over the years, been very contributors. We used XBPIOT and DDE-BIF2. I know Jan gave a talk, the previous talk, so shout out to Jan and for keeping DDE-BIF tool going, because it's a fantastic tool. And I want to thank the IMU Able Visiting Scholar Program, which enabled Bhutan to visit us. And then, of course, other funding. And thank you very much for your attention.
Thank you very much, Sue-Ann, for this very nice overview. Of course, I would say many decades of research.